Hello, AP Calculus. Due to my absence, I wanted to be able to flip the first section in Chapter 4, which is going to be applications of derivatives, just to make sure we didn't fall behind today. There's a lot of definitions and talking and stuff, so I figured it'd be a good lesson that we could probably flip together. Won't be too long. I figure I'll just do the first little bit of intro, and then you guys could finish up by reading the rest of the section and then trying some of the homework problems. If you haven't already, if you guys could just please give the problem set to the substitute, I want to make sure I can look at those and give those a grade. So go ahead and do that now if you can. Also, if you have headphones in your backpack, go ahead and pause me so I'm not distracting to other people who might be in a different place in addition to you. But I'd like to go ahead and start Chapter 4, Applications of Derivatives. We're going to be about 2 days in each section. It might spill over. Some of the stuff in Chapter 4 might take a little longer, but I'd like to see if we can wrap it up in 2 days. We're going to do 4.1 and 4.2, and then we're going to take the 4.1, 4.2 quiz right after that. So Section 4.1 is titled Extreme Values of Functions. So there's a few things that we kind of have to consider when we're talking about extreme values of functions. So we're going to go ahead and make sure I define everything for you so you know what I'm talking about when I say extreme values. The first thing you have to understand is there's two types of extreme values, and the first one we're going to talk about is absolute. Absolute is usually the harder of the two to figure out because functions often have crazy, wacky end behavior, and so absolute extremas can be really difficult. But here's the definition of absolute extrema. Also, sometimes it's known as global extrema. They mean the exact same thing. Let f be a function with domain D, then f of c is the absolute max on D, the domain, if and only if f of x is less than or equal to f of c for all x in D. In other words, it's the highest point on the function in its domain. Absolute min, lowest point on the function in its domain. Often we don't even use the word absolute or extrema. If I say absolute maximum, I'm really probably just going to word it as maximum. An absolute minimum is really just going to be worded as minimum. So if you see on a test I'm writing what's the max or what's the min of the function, I'm referring to the very highest or very lowest point. Sometimes functions fail to have a max or a min. They could have discontinuities, like the parabola with the open-down parabola with the discontinuity right there in the vertex, and so that particular function would have an absolute minimum. Things like that. So that can happen, and we'll kind of look at that as well along the way. So the extreme value theorem is basically a really, really important theorem, and if you're keeping track in the Schachter Book of Awesomeness, this guy is number 2. Mr. Schachter's second favorite AP Calculus theorem. Yay! We're going to get to the first one very soon. The extreme value theorem is extremely important in verifying the existence of extrema. And it says, if f is a continuous function on a closed interval, so it's really similar to mean value. We're talking continuous, we're talking closed interval. Those conditions have to apply in order to use the extreme value theorem. F has both a max value and a minimum value on the interval. Take this for example. Here's cosine, here's sine. If you look at cosine right here, cosine, this is a closed interval from negative pi over 2 to pi over 2. This has a tie for lowest value, minimum value. It's at 0. That occurs at negative pi over 2 and pi over 2. And the max is at 1. And that occurs at x equals 0. And then the sine function over here has a minimum at negative 1 when that's x equals negative pi over 2. And then over here at the top has a maximum value of 1 at x equals pi over 2. So as long as you have a closed interval and the function's continuous, it's always going to have a maximum and it's always going to have a minimum. Okay, that's the extreme value theorem, very important. Here are a couple of examples. In this particular example right here, in the left, you've got a function, and it has this point right up here, which is going to be x sub 2 comma m, this one right here. This is acting as the maximum of the function. And then over down here, x sub 1 m is asking, this right here is the minimum. So you'll notice that the maximum and the minimum of this particular function both occur on the interior. So they're not the exterior, meaning the endpoints. Okay? If you look over here, at this particular function, this is just like a little branch of a parabola almost, and this time both the maximum value, which is right up here, this is the max, and over down here, this is the min, they occur at endpoints. So this is not on the interior this time, which is completely okay, because according to the extreme value theorem, it doesn't really matter where they are. As long as it's a closed interval, it's going to have at least one max and min. This particular example is one of each. This has a max on the interior, and the minimum function, which is over here, right here, is going to be on the exterior. And over here, this one has a minimum on the interior and a max as an endpoint. Okay? So that's basically the idea. Those are pretty much the only four scenarios that can occur. They're going to just basically be somewhere on the parabola or the random curve, whether it's the interior or the exterior. Also, I cannot pause this, so if I make mistakes and start to babble over myself, well, you just have to deal with it, basically. That's that. Local, relative, extreme are the other values. So you've got your absolutes, and you have your locals. Your locals are just simply in the neighborhood. So they're your maxes or mins in the neighborhood. I kind of think about it like a viewing window. Like if you were to look at a particular viewing window, where would your maxes and mins be? Same exact definitions for absolute, except the one difference is obviously you're talking about an interval instead of the entire domain of the function. Note, a function has a local max or a local min at an endpoint if the appropriate inequality holds for all x in some half-open domain interval containing c. So it is possible to have the local max or the local min at the endpoint if that criteria is satisfied. Okay, absolute extrema is also a local extrema. So basically, if I ask you for a list of all the extreme values, and I want you to make sure you include absolutes and locals, if I ask it to you in separate questions, for example, list all the local extremas, well, you start and you list them, but you have to make sure also that you add in any absolute extremas as well. Because absolute extremas are also local extremas. Because obviously, if local extremas are in the neighborhood, absolute value is its entire domain. That's just a really big neighborhood, right? So that's the idea. Okay, local extreme value is essentially the exact same thing, but for local extreme values. Let's take a look. If a function f has a local max value or a local min value at an interior point c in its domain, so let's look at them. Here they all are. And f prime of c, f prime exists. Okay, so we got criteria here. We've got that. Then f prime of c is equal to 0. We kind of studied this a little bit in chapter 3. This is basically saying if you have a extreme value, whether it's local or absolute, because remember all absolute are also locals, and the derivative exists, then the derivative at that value has to be 0. It's essentially saying, hey, you're changing from positive to negative or negative to positive. That, by definition, in chapter 3 we learned, means that the derivative at that point has to be equal to 0. Okay, so for any particular value, wherever you are, you're going to have a derivative equal to 0. It's also notable to add that the derivative might not exist, and we're going to kind of study that as well, but that's going to be called, or what we call a critical point, when the derivative doesn't exist and you would have had a max or a min value there. So just something to consider a couple slides later. Actually, one slide later. Definition of critical point. A point in the interior of the domain at which f prime equals 0 or f prime doesn't exist. So, if the derivative is 0 at this particular point, or if the derivative does not exist at this particular point, it's known as a critical point. Okay? It's known as a critical point. So basically, as far as calculus goes, the first step is always going to be to find the critical points of the functions before we can even consider extreme values. We're going to find the critical points. So we're going to be finding undefined values of the derivative or zeros of the derivative. So this is definitely something, if you haven't yet, pause the video, make sure you write this down. This is what we're going to be solving for, zeros or undefined values of the derivative. Critical points are candidates for extreme values. Very important you understand that your list of extreme values does not come from the critical points. You have to test them. They have to actually work out to be extreme values before you can just simply call them all extreme values. So your critical points is just like your candidate list. It's your list that you have to go and you test. Keep in mind that a critical point is a coordinate x comma y. The y value represents the function value, and the x obviously represents the location. Okay? All right, go ahead and do this one problem. We'll kind of end off here. We'll start the conversation, and you guys will have the tools necessary to go and start some of the earlier homework problems after you go ahead and take a look at this example. So it says, find the extrema of the function 1 over the square root of 4 minus x squared. Okay, so obviously, first of all, we have to worry about this. We have to consider the domain of this function. So keep in mind that this particular piece right here, we'll use a sweet highlighter. Here we go. Boom. This particular piece has to be greater than 0 because obviously it's a radical. So it can't be negative. And it's on the bottom, so it can't be 0. So to figure out the initial domain of this particular problem, the domain is going to be what values make this particular thing greater than 0. So this is pretty easy to solve. X squared is equal to 4. So x is equal to plus or minus 2. And that gives us a domain of negative 2 to 2. Okay? So that's our domain. So it's an understood domain. We have to make sure we use this in the process of solving this problem. So we have a domain restriction. Okay? So that's always the first step. If you have a function with a wacky domain, you have to figure that out, and you have to make sure you take that into account. All right? Well, now let's go and have some fun. Let's go ahead and figure out why calculus is going to be useful. So here's the original function. So f of x is equal to 1 over the, what does that say, the square root of 4 minus x squared? Which, of course, is the same thing as 1 over the square root of 4 minus x squared, is just, 4 minus x squared to the 1/2 power. Which, of course, is 4 minus x squared to the negative 1/2 power if I were to just move it up. So we're going to go ahead and make that quick edit. There we go. There we go. And here we go. And boom, there it is. Now let's go ahead and take the derivative, because remember, critical points come from undefined values of the derivative and zeros of the derivative. So here we go. F prime of x is equal to negative 1/2 4 minus x squared to the negative 3/2, and we're going to remember to chain by multiplying by the derivative of the inside, which is negative 2x. Okay? Now if I were to clean this thing up a little bit, this is equal to, let's put this on the bottom. Let's just keep the 2's are going to cancel. Let's keep the x on top, and let's put the 4 minus x squared to the 3/2 on the bottom, and the negatives are gone, the 2's gone. It looks like that's my derivative. Okay, two things to ask myself. One, when is this derivative undefined? So, f prime of x is undefined when 4 minus x squared equals 0, right? So obviously this is the only thing you have to worry about, and f prime of x is undefined when this is equal to 0, but obviously we kind of ruled that out of our domain initially, so we don't have to worry about it. Let's go ahead and take a look when f prime of x is 0. Well, there's only one particular value that's going to make that derivative 0, and since the numerator is x, that's going to be the only one. So when x is 0, this is going to be the only particular point that makes this whole entire function equal to 0. So that's the only critical point, right? Because the undefined values are excluded from our domain because they were negative 2 and 2. We already figured that out up here. And then there's only one other value that makes it 0, so there's one critical point. Yay! So we've got one critical point. Okay, the goal now is to figure out, is this actually an extreme value? And to do that, you need to make a sign chart for your derivative. So, sign chart is used for the derivative, okay? It's a common mistake to make a sign chart for the original. You want to make a sign chart for the derivative. So the extreme value goes in the middle. We're going to test numbers higher and lower than that and place them in the function. Well, let's start with the number like, less than, or we'll do greater than 0 first. Why don't we plug in 100? You plug 100 into this function, what's the sign? Well, on the bottom here, you've got 4 minus 100 squared, which is going to be a really, really, really large negative number, but you're raising it to the 3/2 power, which is in return going to input out a positive number. So you have a positive 100 divided by a really big number. The moral of the story is this thing's going to be positive. And you do the same exact thing for a negative number. Well, the bottom still spits out a positive number because it's being raised to the 3/2 power. And then you have the negative 100 on top, or whatever we were testing, and you come out with a negative number. This sign chart for the derivative proves that there actually is an extreme value located at 0. The evidence is the fact that the derivative changes from negative to positive. Okay? So this tells us that f prime of x changes from negative to positive at x equals 0, which means 0 is a extreme value. Okay, so x equals 0 is an extreme value. Now there's two other things to figure out. The first is to figure out the corresponding y value. Well, that's pretty easy. We just have to take 0 and plug it into the original. We go back to the original. You plug 0 in here. Let's do it right up here. F of 0 equals 1 over square root 4 minus 0 squared is just simply 1 over the square root of 4, or 1 over 2. So f of 0 is 1/2. So I'm going to go back down here. So we're going to go right here. We've got 0, comma, 1/2. Okay? So this is the critical point. But now the question is, well, is it local? Is it absolute? Is it max? Is it min? Well, let's go ahead and figure out if it's max or a min first. We have a change from negative to positive slope. So basically what we have going on here is, I'm just going to use linear functions to demonstrate. Negative slope to positive slope. So what we're dealing with here is definitely a minimum value of some sort. It might be an absolute minimum. It might be a local minimum. Well, here's the thing that's interesting. There's only one critical point, right? So if this thing is decreasing indefinitely and then increasing indefinitely, this point, 0, 1/2, actually has to be an absolute minimum. An absolute minimum, okay? The only other point, the only other time that this might be just a local would be if this thing had more than one critical point, because then it might turn around and dip down below even lower than it was before. But that's basically the idea. This thing's going to go down, 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 and it's going to get to its lowest point, which is 0, 1/2, and then it's going to increase indefinitely. It's going to basically go up and never be able to get lower than the value of 1/2. So 0, 1/2 is a minimum value. It is an absolute minimum. But remember, you don't really need to use the word absolute. When you write the word minimum, I'm assuming you're talking about absolute or global, whatever you want to call it. So that's basically the minimum value. All right? That's 4.1 in a nutshell. What I would say to do now is to go read 4.1. No, not copy paste. 4.1, negative 4.1. You guys have to read section negative 4.1. Now read 4.1 in the text. And then start some of the homework problems. Okay? I'll post further directions on the planner, and thanks for watching.